So for today's video, we're going to talk specifically about the quantity of heat, not just the way that heat causes a system to change. So a little bit of a review. We know that matter changes phases, and when matter changes phases, it requires the exchange of energy. So in our icy hot lab, on a hot plate, we caused ice to melt, water to warm up, and then the water to boil. Well, there's a specific quantity of energy that's equal to those particular changes. And there's two equations that we're going to use to be able to solve that. One of the constants, or one of the number values that we're going to use, is something called the specific heat. And so I wanted to spend a little bit of time to talk about what that was and explain some of these values and how they mean, especially in terms of units that look kind of weird like that. All right, so specific heat is the capacity required to raise the temperature of 1 gram of a specific material, and that's where that term specific comes from, because it's specific to the type of material that we're heating up or cooling down, by 1 degree Celsius. So we're looking at a certain energy value, again, according to the material, that you need to apply if you want to make 1 gram increase 1 degree Celsius. And then there's multiples of that. If we have 100 grams of the substance and we want to go up more than 1 degree, that's where this constant comes in as a multiplier for our equation. So the specific heat symbol is a lowercase c because it's a capacity, and the units for that is the amount of energy, joules, per gram of material temperature change. So it's a combination of the three values that we need to equate in order to determine either the energy required, the mass, or again, the temperature change that we want. So off to the right here, we've got a bunch of random materials: water, ice, water vapor, sand, iron, copper, and lead, and then the heat capacities that are connected to those materials. And so you notice that our heat capacities can be anything as great as around 4, and then even down into the decimal values of 0.13. And so what these numbers and this constant is really telling us is, again, that energy requirement. So if sand has a specific heat of 0.83 joules per gram degree Celsius, that's saying that if I apply 0.83 joules of energy to 1 gram of sand, its temperature will increase by 1 degree. Now that could be applied 0.83 joules of room temperature sand, and it goes from 20 degrees Celsius to 21 degrees Celsius. Or I could apply another 0.83 joules of energy and cause warmer sand at 30 degrees Celsius to increase to 31 degrees Celsius. It's the same amount of energy for each degree change for the size of the system that we're trying to change. Okay? So when we compare some specific heats, things like sand versus water, that energy capacity helps us to understand why in the same system certain things feel different temperatures. So if you've ever gone to the beach in the middle of summer at noon on a really sunny day, you wind up burning your feet on the sand, but you feel a cooler temperature when you get into the water. Both systems are experiencing the same amount of energy because the sun is beating down all of this thermal energy across the surface of the earth. Well, the reason why the sand heats up to a higher temperature is because it has a smaller energy requirement. The reason why the water heats up to a lower temperature is that it needs more of that energy from the sun. It has a higher capacity to change its temperature. So which will heat faster, sand or water? The sand, because of its lower specific heat capacity. Okay, so just kind of a nice little example rationalizing why these numbers are going to affect that system. So there's some actual numerical data that we can use to crunch out one of the missing components of this equation. So Q, again, is our symbol for energy. And the units that we're going to use for energy is the joule, or capital J. M is going to represent the mass of our system, which we're going to weigh out in grams. C is that specific heat value. And the units, again, are that weird combined units of joules per gram degree Celsius. And for temperature, we're not so much interested in what the current temperature is of a system, but how much the temperature has changed. So this little triangle here represents the Greek letter delta. And in mathematics, that Greek letter delta represents change. So delta T actually stands for the change in temperature. Now we're still going to measure our temperature in units of degrees Celsius, but the way that we're going to calculate delta T is we're going to say T final minus T initial. So what was our ending temperature if it warmed up or cooled down minus our initial temperature? And it's always going to be final minus the initial because we want to look in terms of where did we end from where we began. All right, so let's do some practice problems using this Q equals MC delta T. It says how much energy, so we're solving for Q, must be added to a system that has a mass of 250 grams. It's a sample of lead, and the temperature change of that lead is from 40 to 90 degrees. So we're going to use Q equals MC delta T. Again, we're solving for Q. Our mass is 250 grams. Our delta T is T final, 90 degrees Celsius minus 40 degrees Celsius. And then this heat capacity, we're told it's a sample of lead. Well, lead has a particular specific heat capacity of 0.13, and that's something that's very specific. It's because it's a lead sample, so it will always have that same value for lead. Okay. Now, I will also mention at this point, there's no point in having any of these values memorized. These two are the most common that we're going to use over and over again, so those become kind of stuck in your brain just from using them so much. But there won't be any questions on your test about like, well, what's the specific heat of copper? That's a value that you'd have to be provided or solve for in a particular question, right? So now that we've got the mass, capacity, and the temperature change, we're going to solve this equation to find out what Q equals. And the first thing we want to do is do this simple subtraction to get 50. So T final, 90 minus 40. And then it's mass times capacity times this temperature change. So we'll do 50 times 0.13 times 250, and we get a Q value equal to 1,625 joules. Okay, again, the whole point to this unit is that when grams multiplies and there's grams here in the denominator, that's going to cancel out. And when degrees Celsius multiplies, that's in the denominator, so that's going to cancel out. So this is really just our numerical converter to convert a mass and a temperature change into the energy for that particular system. Right? So for the last problem, we are looking at 435 joules of heat added to a 3.4 gram sample of copper, and it's starting at 21 degrees. We want to know from the addition of that heat, what temperature would it end at? All right, so I'd encourage you to pause the video, plug in the values into the appropriate spot on the equation and see what you get for a final temperature, and then resume the video to see how well you did. All right, so I always start with the equation, and then we have a joule value, so there's a certain amount of heat, so we've got 435 joules equal to this 3.4 gram sample of copper. And again, because we're working with copper, we've got a capacity of 0.38 joules per gram degree Celsius. And we want to find final temperature from that starting point of 21 degrees Celsius. So while it's not as easy to solve as this first equation, we only have one variable and we just have to solve for this carefully, right? I would start by simplifying this because this is multiplying to this final equation. And then we're going to divide this over to this side. So really it's going to be 435 divided by 3.4 times 0.38. And then that whole side is going to cancel out. So 435 divided by 3.4 divided by 0.38 is equal to 300, and we'll say 37. And now all we have to do is add 21 degrees to both sides. And so we'll say that T final is equal to 358 degrees Celsius. Okay? So again, copper has a really small capacity or requirement for heat to change its temperature. So the fact that we've got a small mass, each gram only needs 0.38 joules to raise it a degree Celsius. We're applying 435 joules. So we're putting a lot of energy into something that has a small capacity, so we're going to see a huge temperature change for the end result. Okay? So this is one equation that we're going to use, Q equals mc delta T, but we have to recall that on our energy diagrams, we had segments where the temperature didn't change. So we have a second equation that we're going to use that looks very similar but has two different constants attached to it. All right, so this is Q, our energy, equal to the mass of our system, same system, times H, which are these heat constants. So we've got here the heat of fusion of water and the heat of vaporization of water, right? So heat of fusion is specifically referring to the point at which water is either melting or freezing, and the value associated with that is 334 joules per gram. And the heat of vaporization for water is when water is evaporating / condensing, and the value for that is 2,260 joules per gram. So you notice that these units, kind of similar to the heat capacity, except it doesn't have degrees Celsius because this is the value or the constant that you use at the point where there's no temperature change. So how much energy must be added to a 250 gram sample of ice at 0 degrees Celsius to melt it into water at 0 degrees Celsius? So quickly, I want to talk about when we're going to use each equation, and then we'll get to these practice problems. And that first one will make a little bit more sense. So in terms of an energy diagram, we've got this generic shape, and we've got our solids, liquids, gases. And remember, from this segment to this segment, here to here, and here to here, we're increasing in the y-axis, which is our temperature. So for this segment, and this segment, wherever there's a temperature change, we're going to use, we'll do this as my key, Q equals mc delta T. But there's two segments that go completely horizontal and move only across the x-axis, which is energy added, and this is where we're melting or freezing at a constant temperature, and where we're evaporating or condensing at a constant temperature. So in these two segments, where our thermal energy is constant, but our phase energy is increasing, we're going to use, Q is equal to M times H. Right? So basically when your temperature is not changing at all, we have to use the equation that uses a different constant for when the temperature is constant. So in this first problem, it says how much energy must be added to a 250-gram sample of ice at 0 degrees Celsius to melt into water at 0 degrees Celsius. So on an energy diagram for water, where this phase right here is at 0 degrees Celsius, you're starting here, you're ending here, so there's no temperature change. So we're only going to use one equation because we only go across one segment of our energy diagram. So because this is melting, we're going to use H sub F, and we'll use the equation Q equals M H sub F, and the energy is equal to the mass of that system times the heat of fusion constant, 334. So 250 times 334, we get 83,500 joules of energy just to melt a sample of ice. Okay? If we have how much energy must be removed from 1,200 grams of water vapor at 100 degrees Celsius to condense it to water at 100 degrees Celsius, again with no temperature change. Here we're removing energy, so this has to be on a cooling curve. And the cooling curve for water has condensation happening here at 100 degrees Celsius. So we're starting at 100-degree water vapor, ending at 100-degree liquid water, and we're just talking about the energy amount that's being removed just to go through that process of condensation. It's a very similar process, except we're going to look at Q equals mH sub V, because that's the heat of vaporization constant. And so Q now is equal to 1,200 grams times 2,260 joules per gram. So 1,200 times 2,260, we get a whopping 2,712,000 joules. But this is energy being removed. So remember, when energy is gained, it's a positive value, and when energy is lost, it's a negative value. So this is actually a negative amount of energy that's being taken out of that water vapor and put into the environment, or taken out of that system. Right? The last one has us use both equations. It says how much total energy, total, must be applied to 500 grams of water at 35 degrees Celsius to warm it up and boil it away entirely. So on an energy diagram, we're heating it up, but we're starting as a liquid here at about 35 degrees, and we have to heat that water up to 100 degrees and then boil it away entirely. So we've got two segments of this energy diagram that we're going to change through. So that means there's a certain Q value associated here, and there's another Q value associated there, and we have one equation when there's a temperature change and another equation when there is not. So we're going to start with this first equation here. We'll call it Q1. So Q1 is equal to MC delta T because of our temperature change, which means it's equal to the mass of our water times the specific heat of liquid water times the temperature change, which is 100 minus 35. Because we're starting at 35 and we got to warm it up to the boiling temperature before it boils away entirely. So we'll do 100 minus 35. Delta T now is 65 degrees times 4.18 times 500 gives us a Q value equal to 135,850 joules. Now that's just to go from here to here along the x-axis. So to solve for Q2, where our temperature is constant and the added energy is causing it to boil away entirely, we have to use mH sub V for vaporization. But we're going to use the same mass because we don't lose any. law of conservation of matter, times the heat of vaporization constant for water, which is 2,260 joules per gram. So now we'll do 500 times 2260, and we get another large value of 1,130,000 joules. Now again, that's just to go from here to here, Q2. The total amount of energy is both the amount to heat up the water and the amount to boil the water. So we have to add the two together. So this plus 135, 850 gives us Q total equal to 1,265,850 joules.